Okay, good afternoon, everyone. So my name is Steven. So right now I'm a PhD candidate in analytical chemistry at the University of Toronto. As we all know that the recent pandemic, the COVID-19, caused a lot of school closure. And one kind of class we would like to provide free lesson for everyone in order to make sure everyone keep up to your study. Okay, so for today, from 2 to 3, we will go through our first year university general chemistry, and then we will start with a chemical foundation. Uh, you may see that I will turn my head to the lab because I have my screen on the lab, so just don't feel weird about that. Okay, so I think we can start our lesson today. All right, so I just repeat. So today we're going to go through our first year general chemistry. And today we'll start with the first chapter, chemical foundation. So it's all the foundation you need in order to start your first year chemistry. So we can go through the syllabus. So first of all, we will have our looking at the scientific method, the unit of measurement. Second will be uncertainty in measurement, and then we move on to significant figures and correlations, also with dimensional analysis. If we have enough time today, we also go through temperature, density, and also classification of different matters. Okay, so let's start with our first topic, the scientific method, the unit of measurement. Um, Chemistry is a practical science, so we have to do a lot of experiment, have to take a lot of measurement. For example, we can measure the quantity of solute in a solution. We can use concentration. We can measure the weight, how heavy is it for a particular reactant. We also can measure the volume or gas, something like that. So that's why we have to understand, okay, what will be the unit of measurement we are going to use. Okay, so we have a concept we will. Okay, first of all, for scientific measurement, they always have a scale and unit. Scale means they have a number. Unit, they have a corresponding unit to tell you, is it a mass, is this a concentration, is this a volume. And then we have a unified unit system. So we call the international system or the SI system. So for each of the, you can say, quantity, each of the different physical properties, they will have a corresponding SI unit, and we have to remember to use different SI unit for different quantity. So, for instance, for mass, I mean, the first thing when you start your chemistry lab, you're going to measure a particular amount of reactant. So, for instance, you need, say, one teaspoon of salt. Of course, 1 teaspoon is not a standard international unit, but the standard unit we're going to use is kilogram, in kilogram. Okay, sorry about that. Okay, kilogram over here. And then for weight, so if you actually think about that, mass and weight, they sound a little bit similar. So we are going to start with mass. At the same time, we also hear about weight. So actually, what's the difference between them? Okay, so I'm okay. So let's start with mass. So the mass is a measure the amount of matter in the body, and the measure of the resistance of an object offered to a change in the state of its motion. I think I have to move. I have to move to talk about the physics. If you remember, the Newton, I remember should be the uh, first law. I'm not really good at physics, but at least we know that force equals to ma, and the force applied to a body equals to a mass times a constant, not a concentration, acceleration. Okay, so in other words, when you applied a force on a mass, for example, we have mass of a square, and then we have a frictionless surface, and then you apply a force. When you use your finger to apply a force, you should feel a bit resistant, or you feel a bit heavy to push that mass on top. And this resistance requires the mass. Okay, how about the weight? So essentially, the weight is different from mass by definition, but the weight is the force exerted by the gravity on an object to measure mass. So in other words, the weight it will be depend on the gravitational force. So they are not equal. For instance, if uh, we are on Earth, right? We are on Earth. So say let's say I'm 60 Newton. So because for Earth they have a different gravitation pull. But when I move to Mars, so say when I go to Mars, yeah, the gravitational pull will be lower. So I may have a weight become less. Okay, right now just making a number. I didn't do an exact calculation, but I just want to show you the weight will depend on the gravitational force or gravitational pull, or it will depend on the planet. Okay, so I already explained that. So what would be the difference, the mass, the weight? So for the again, just to repeat to remind you, for the mass, it will measure the amount of matter body and the resistance of object towards a change in state of motion when experiencing force. And very important, the SI unit will be kilogram. Will be kilogram. And for the weight, it's the force exerted by the gravity on object to measure mass, and the weight will be vary with the strength of the gravitational pull or gravitational field. Because it's related to the gravitational force, so the SI unit will be Newton. Newton. But again, in chemistry, we only need to worry about the concept of the mass, and also we're looking at that to be kilogram for the unit. Okay, so when we have the SI unit to be kilogram, we can go measure everything. And then we can have different value. For instance, you can measure something really, really light. For example, our maybe even go to an atom, maybe a dust, maybe a very small particle. Then the mass can be very, very small. For instance, we can measure maybe 10 to the minus 9 gram. Again, gram is not the SI unit. It's not the SI unit. So therefore, when we convert it to kilogram, we should have 10 to the it should be 10 to the minus. Let me do a rough calculations. 10 to the minus 12 kilogram. Okay, but I mean every time when you have to tell other, for example, other scientists or even your classmate that you measure really, really light mass is 10 to the minus 12 kilogram. It's just it's so complicated. It makes things so complicated and so redundant. So that's why we are going to give different name to different quantity of the mass, or maybe to the number. So what I mean is that, for instance, over here we have 10 to the minus 9 gram. Can we sort of convert 10 to the minus 9 this number to our English name? So in other words, we are going to convert that to nano. So for this case, we have nanogram corresponding to ng. Just like the question over here. So what would be the name of the unit? So because of 10 to the minus 9 grams, so we have nanogram. So we have nanogram over here. Same as kilogram. So for kilogram, it just means that 10 to the power of 3 gram. And that means kilogram. It means kilogram. Same thing again. Same thing also for if you look at maybe the distance, 10 to the minus 3 meters. 10 to the minus 3 meters. So in order to make it easy to communicate, we just give it a name called mini. So we call meters. Okay, so in other words, we can change the name of the unit in order to help us to convey information to another scientist or even your classmate and other people much more easier. But if you pay attention, as I told you, the SI unit is kilogram. So SI unit is a kilogram over here. But again, in chemistry, the proper SI unit we should use is kilogram. But most of the time we do our chemical reaction, they will be small quantities, so we can use gram, nanogram, and sometimes microgram. So we can have milligram 10 to the minus 3, we have a microgram 10 to the minus 6, and then we have nanogram 10 to the minus 9. They are commonly used in chemistry, but they are not the SI unit. I just want to remind you. So because it's just by convenience, this is the scale that we always, or most of time, even for gram, most of the time that we handle in chemistry. But that's why in chemistry you will see gram, milligram, microgram, and nanogram, but they are not the SI unit. They are not the SI unit. If you are told to express all of the weight in SI unit, you have to do a conversion to kilogram. Yeah, I just want to remind you about that. Okay, so we can keep going on, keep going. All right, so for different parameter, so for example, name, time, mass, and temperature, they were corresponding SI unit, corresponding SI unit. So what would be the SI unit for name, time, mass, and temperature? Okay, so here are the SI units. For name, we are looking at meters. So will be m. Time will be seconds. Mass will be kilogram. Temperature, we are using Kelvin instead of degree Celsius or Fahrenheit. And then for the amount of the substance, we are going to use mole, or you can say number of moles. Okay, so they are the SI unit, but again in chemistry, it would depend on what field of chemistry you are working with, and we will be use a slightly different unit from the SI unit in order to make our life easier. But again, if we are told to use the SI unit to express all the result, we have to use all those units instead of other units. For example, milliseconds, microseconds, millimeters, microgram, etc., or millimole, etc. So, just want to remind you again. Okay, so we have an idea of the SI units that we use in different physical quantity when we're actually doing experiment in chemistry, and then we can proceed to look at unit conversion. A little bit look at unit conversion. So from question 2, the Earth oceans contain approximately 1.39 times 10 to the power of 9 kilo meter cube of water. Calculate the volume in liters. The volume in liters. Do we have volume over here? Okay, so we don't have volume. But for the SI unit of volume, it will be liter. It will be liter. So because we have a unit that is not in the SI unit, so we have to convert that to SI unit. So first of all, we have to know the conversion factor. The conversion factor, most of the time is given. Sometimes you have to memorize that. But for this question, it's already given. So we know that 1 liter equals to 10 to the power of 3, 10 to the power of 3 meters. This should be meter to power of 3, so the meter cube, because they both are volume. So they should be the unit should be consistent. And I will also talk about more the consistency in the unit in dimensional analysis. Okay, so we know that 1 liter equals to 10 to the power of 3, or 1,000 of meter cube. So we can do a unit conversion over here. Okay, so yeah, we have that much for unit conversion, and that it would be corresponding to 1 kilometer to the power of 3. And then essentially for each 1 kilometer of cube equals to 10 to the power of 9 to the meter cube. Okay, so in other words, from here we know that for every 1 kilometer cube equals to 10 to the power of 9 meter cube. And then we have that many of kilometer cube. So that's why we have to multiply our volume by the conversion factor over here to convert that to minicube, and then convert minicube to 1 liter or 2 liter. And then after all those calculations, we should be able to see that is equal to 1.36 times 10 to the power of 21 liter. If you are confused about the calculations, I'm going to show you the detailed calculations. Personally, I don't really like the solution over here because they just put everything together. It doesn't explain that really well. Okay, so first of all, we need a conversion factor between from kilometer cube to meter cube to liter. we have to know the conversion factor for this conversion and also for this conversion over here. Okay, so first of all, we have to figure out the conversion factors. Okay, since we are already given the conversion factor over here, so we know that 1 liter will be corresponding to 10 to the power of 3 uh, meter cube. So we have a conversion factor over here. And so in other words, we can also further convert that to be a ratio. So we have 1 liter to 10 to the power of 3. Sorry about that. Just give me a second. All right. Okay, there we go. Meter cube over here. Since we have a ratio, so we can convert this ratio to a fraction. So this is essentially equals to 1 liter divided by 10 to the power of 3 meter cube. Yeah, we have a ratio like that. Okay, at the same time, what would be the conversion factor from kilometer cube to meter cube? So we know that 1 kilometer cube will be corresponding to 10 to the power of 3 kilometer cube. Sorry, I made a mistake. So instead of we convert from kilometer cube to meter cube, we have to further do another conversion as well. Okay, so because it's 1 kilometer cube, so what would be the corresponding number of meter cube? Okay, as we know that 1 kilometer equals to 1,000 meter. So 1 kilometer cube should be equals to our 1,000 meter to the power of 3 to the power of 3. So in other words, from our calculation over here, we should be able to find that it should be equals to 10 to the power of 9. So that's where it's come from. This is where it comes from. This is just a conversion factor from meter cube or to kilometer cube or the other way around. Okay, so again, we can write another ratio over here so that we waste everything that's not necessary. Okay, so we have 1 kilometer cube to 10 to the power of 9, and then equals to 1 kilometer cube 10 to the power of 9. Okay, so we will have two ratios over there, and then we are going to do the unit conversion by two times. So the first time will be from here to meter cube, and then meter cube to liter. All right, so we have a value over here. Let me move on top over here. So we have 1.36 times 10 to the 9 meter cube, and we want to convert it to meter cube. And then we know that you can see that this is the ratio over here. 1 kilometer cube corresponding to 10 to minus 9 meter cube. So we have to multiply this ratio. Okay, but when we multiply this ratio, how are we going to arrange that? Because we can arrange 10 to the power of 9 meter cube over 1 kilometer cube, or 1 kilometer cube over 10 to the power of 9 meter cube. So which will be the denominator, which will be the on the top? But this ratio can be right the other way. It can be 10 to the minus 9 to 1 kilometer cube, something like that. So that's why the fraction will be different. Okay, so how can we arrange that? Actually, it's pretty easy. Okay, so first of all, what we want to do, we want to convert our kilometer cube to meter cube. Okay, so we are going to rearrange the conversion factor, the fraction, in a way that after you do the multiplication, the only unit left will be meter cube. Okay, because we start with kilometer cube, so in other words, we have to have a kilometer cube on the denominator, so we can be cancelled out, and then we can put our meter cube on top, and then it should have the only one remaining over here. So if we cancel that out, we will have 1.36 times 10 to the power of 9 with the unit meter cube. So yeah, it's a pretty long number. Okay, so we already done the first conversion. The second conversion, we're going to convert meter cube to liter. So we are going to do exactly the same thing, so that we remove the everything here. We're going to do exactly the same thing. We have the conversion factor over here, right? And we want liter to be only unit remaining. So we are going to multiply the whole number again with 1 liter over 10 to the power of 3 meter cube. So from here, you can see that you cancel out, and then you can use a calculator, or um, you can simplify the calculation, and you should be able to find out uh, the answers over here. And actually, I just find that I missed the minus 3 over there. Yeah, I missed the minus 3 over there. Yeah, because there's a minus 3. Yeah, but 1 liter to 10 to the minus 3 meter cube, so that's a minus 3. And if you do the calculation correctly, you should be able to find your answers. And this is doing the unit conversion from long SI unit to SI unit. Okay, so this will conclude the first topic on the unit of measurement. So first of all, for each of units of measurement, we have our scale will be a number with a unit, and then for each unit, we are going to use a SI unit for all the measurement. And you have to remember for which kind of physical quantity they use which SI unit. But again, I also want to remind you in chemistry, again, it would depend what kind of experiment you're doing, in what field of chemistry you are working on. SI unit sometimes is not that helpful. It's not that common. Sometimes we use milligram, microgram, etc. Although they are not the SI unit, but they are pretty common to be used in chemistry. So that's why we also have to know how to convert our long SI unit to SI unit in chemistry. Okay, so when we move on to the second topic, uncertainty in measurement. So when we move on to talk about the uncertainty in measurement, we will talk about the precision, accuracy, etc., something like that. So, but why do we care about that? Why do we care about that? Actually, uncertainty is very important. But when we're doing experiments, for example, very simple experiment that you're going to measure a mass of a for example, you have a reaction substance, and then you give off a gas, and then you're going to measure the mass. Or at the same time, you can put it on the balance. You will give you a number. For example, it would be a 5.0 gram, something like that. Or you can actually measure the length of a piece of metal. For example, it's a silver. For example, it's a silver, anything is solid metal, and then measure the length, and they find it's 15.1 centimeters. Yeah, we can do a lot of different measurement, and also we can use different equipment to do the measurement. Okay, but why are we going to use different equipment to measure the our for example, the length? But for our length, we can use a ruler. We can use you can use a ruler. You can use maybe your phone. You can use anything that can help you to measure the length. Sometimes I even use my credit card to measure the length. So from different measurement equipment or different equipment, they will have associated uncertainty or associate. I would say associate uncertainty or the limit of the information they can provide. For instance, if you use a ruler, say you have a ruler, you can have 1 centimeters, 2, 3, or 4, etc. And then sometimes they have maybe 0.5, something like that. So the marking will tell you the limit, of the information of your ruler that can tell you. So for instance, the smaller units over here will be 0.5 because you can measure down to 5 millimeters. 5 millimeters. So if you have for instance, if you're more trying to measure a coin, it just happened the coin like that. It's just between the 0 and 0.5. Between 0 and 0.5, there are no marking at all. So you just don't know what exactly what exactly the measurement will be. And this will give rise to the uncertainty in your measurement. And same thing happens for other equipment, for example, the mass over here. So assume your balance only can give up to one decimal place, and assume you have a godlike power. You know that the mass is 5.01119 gram or 0.11 gram, but this is your balance giving you. The balance giving you. Your balance cannot give you any more information beyond the second decimal place, second or third decimal place. So those information will be lost. At the same time, there will be an uncertainty introduced to your measurement due to the limitation of your equipment, because it doesn't really tell you is we still have 0.0111 gram at the bottom. Behind the zero, but it just cannot tell you. So in other words, when you're actually looking at this measurement, it could mean 5.01, 5.02, 5.09, etc. Because there's an uncertainty over there, and the uncertainty will be plus and minus 0.01 gram, something like that. So that's why uncertainty is very important in doing experiment, because we have to know how much information we have, and what will be the limitation of the equipment when we are doing experiment, and what will be the impact on our accuracy of our result. Okay, so I think I have enough talking. We should keep moving. Okay, so in order to define the reliability of a measurement, we use two different terms: accuracy and precision. So let's look at the slide over here. The accuracy will be with the agreement of particular value of a true value. Precision will be with the extent of agreement between measurement of same given quantity. Yeah, sound kind of makes sense. For example, let me try to aim at the center with the arrow, and how close the arrow reach to the center is the accuracy. Okay, for precision, we aim at the center, and how close the second arrow, which will be according to the first arrow, is the precision. Yeah, it may kind of make sense. It kind of makes sense, but it's just a little bit confusing. Okay, so because you can see, using arrow and a target. So again, we can use archery as an example. So I hope some of you may try archery before, and you should be able to see that. Sorry for my drawing. My drawing is really bad. So we have a target over here. We have the 10-point target at the center. Then we have 9, and then we have 5, etc. Yeah, this is really ugly looking target. Okay, so here's our target. As soon you're going to this is me. I am doing a draw. Okay, draw a draw, and this should be an arrow over here. Alright, and then I'm going to shoot to my target. Shoot to my target. Say I have 5 chances. I have 5 arrows. 5 arrows. Okay, so I try to shoot. So again, I draw another target after I have my 5 try. Okay, the center is everyone that want to aim at, because the 10 point, the highest point, everyone want to get it. So I aim for that point, and then I have the first hit, I have the second hit, I have the third, 4, and 5. So I hit, 5 of them. I'm not really a pretty good shooter, so didn't hit the center, but I just hit somewhere around it. Okay, so can you tell me if my okay, sorry for my handwriting as well. I'll try to write slower. Okay, so can you even comment on the accuracy of my arrow? And also the precision of my arrow. Okay, so when we talk about accuracy, we must have a reference value or a true value. Reference value or true value, pick any one of them. This will be a point. That's the golden point. So for instance, the golden point that I always want to hit will be at the center, and this will be our true value, the reference value. And the accuracy of each shot will be corresponding how far for each shot from the true value. How far is to the true value? Okay, so from here, yeah, we are looking at the distance from over here to here, distance over here to here, and distance over here to here. You can plot it, and you can say that um, I'm not that accurate because I didn't hit that close. I just hit around it and didn't hit um, the center. So I didn't hit the center. If I do an analogy to a measurement, for each measurement we can have a value. For example, 1, 1.5, 2, 3, and 4. And the true value that we want the measurement to be will be say is 3. So it's just like the same thing happened over here. I have 1.5, 1, 1.7, 1, and 0.9. None of them is really close to the true value of 3. None of the heat is close to the center, to reference value. So that's why you can comment that the accuracy is low. Okay, so accuracy is how far for each measurement from the reference value and the true value. Then how about precision? Okay, so for precision, if you also look at my heating over here, I keep shooting that. Assume we have a tight gripping. So tight gripping means all the arrow they land pretty close to each other. So each arrow land pretty close to each other. But it just doesn't matter how far from the reference value. It just matters how far those arrows they hit close to each other. So yeah, I think I have a tight gripping, and from this tight gripping, I can say that my shot they are precise. So in other words, the precision is talking about how far your measurement are apart from each other. For example, we have the true value is 3, and your measurement will be 1.1, 1.2, 1.0, 1.1, 1.1. Although they are far away from our true value, the accuracy is low. It's low, but the precision is high because the spread of our measurement is not that far away. It's roughly 1.0% minus 1.1% minus 0.1. So from here, we can tell that the precision is high. Okay, just to recap, for accuracy, we're looking at individual measurement, how far the individual measurement are weight from the reference value or the true value. For precision, we're looking at how far away each measurement spread with respect to each other. Okay, so let's check if you fully understand that. Okay, first of all, we have example 1. So we are doing a measurement of for example, we have some sort of a ball, a crib, anything like that. You're going to measure a sample for 5 times, and then you're obtaining 5 different measurement over here, 2.486 to 2.488. Okay, so can you comment whether it's accuracy or precise? And also you try to determine the accuracy and precision. Okay, so first of all, for this question, for the solution, they are going to ask you to find the FH over here. I don't think it's kind of makes sense over here. Again, because we don't know the true value, and we don't even know if the balance is reliable. Yeah, because I'm kind of skeptical. I just assume the equipment may not be that accurate. So yeah, the solution here, they assume that the true value is at the FH, at the FH. I don't think that's a pretty good way to assume that. So instead of using the FH, I would just say, let's just assume that the view value is 2.486. 2.486. Okay, so when we determine the accuracy, we can determine the accuracy of individual measurement. So you can take the first measurement, compare to your true value, and then you can compute the difference. Same for the second one, third and fourth and the fifth one. But we can also do it the other way, is that we actually found the average, and then compare the average to the expected value, the reference value, or the true value. And then from there, you can assess whether it's accurate or precise. Okay, and then the last thing will be precision and accuracy. Okay, so as you can see that they have 2.486, 487, 485, 44, 488. They're pretty close to each other. So they are actually also pretty accurate. Sorry, pretty precise and also pretty accurate. Okay, so if you pay attention from what I told you, I only tell you verbally how I'm going to 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 tell if the measurement is precise or accurate. But there's a problem. So how can we determine precision or accuracy? Do we have a much more subjective way to do that? Yes, we have. Instead of just looking at the number and then just do a virtual comparison, essentially we have to do some calculation. We should back up our claim with number. That would be much more appropriate. Okay, so let's move on and we can see what we can do. Okay, so another question will be: assume we have a student throw a ball in the air, and then we call the time it takes to fall back to the ground. And then we have 6.2 seconds, 6.0, 6.4, 6.1, and 5.8 seconds. Okay, so first of all, how can we extract the resulting time using the data given? And then, we can look at question 3 later. Okay, so we have individual measurement. If we have individual measurement, they essentially depend on the measurement. We are actually measuring the same event all over time. So say we measure the throwing a ball in the air, we call it fall back to the ground. We repeat for 5 times. In order to express is much more appropriate, we are going to express that as a average. So over here. So we can express that is an average. So the average will be 6.1 seconds for the ball to fall back to the ground. Okay, for the ball to fall back to the ground. Okay, so for this case, you can find a true value, you can find an expect value, and also you can find the reference value. And then you compare the average with the reference value, and then you can tell the accuracy of this measurement. Yeah, not that difficult. And okay, not that difficult. You can find a difference, and then you can also when you find a difference, you can also find the percentage on the difference, and then you can set a threshold for that percentage. For example, 5%. 5% pretty commonly used, and then if the difference between the reference and your measured average is within 5%, then you can say that your measurement is accurate. It would depend on what kind of situation, but most of the time it's 5%. Okay, so let's give you an example. So for instance, we have 6.1 seconds, and our expectation is 6.2 seconds. So we just need to take our you can say take expectation minus the reference, or reference minus the expectation. We just want a difference. So we have 6.2 expectation minus our seconds divide over the true value, and then we can multiply the whole thing by 100%. We can look at the percentage difference. So let me do a real quick calculations. And you should be able to find out that it will be 1.6%. And say I set up the first show is 5%. Anything within 5% difference will be considered accurate. Then we can conclude that our measurement is accurate. Yeah, pretty easy. But how about precision? Okay, so for precision, we have different way to do that. Okay, so first of all, precision, we are looking at how far the measurement, individual measurement, located from each other. So essentially, if you go back to our target over here, and then we doing some heat at the both sides over here, we're essentially looking at the spread of our measurement. So when we are looking at the spread over here, we can use different mathematical methods to describe the spread. So the first one, just like over here, we can look at the highest value and the lowest value and look at the difference between high and lowest. So we know how far the spread will be. So from here, the spread will be 0.6 seconds, and the center point of the measurement should be equal to 6.1, and then we can represent the spread by plus and minus 0.3, because the lowest is around roughly 5.8, the highest is 6.4, the center point is 6.1, so that's why you know that is plus and minus 0.3, because you can go to 6.4 and go down to 5.8. Okay, that's one way of doing that. If you remember, if you took data management or data analysis or statistic, we also have another term to represent the spread. Will be the standard deviation. Standard deviation. Yeah, you can plug in there, find out the mean and standard deviation, and then you will find the corresponding number. Okay, so that's how you compute the spread. But how about precision? Precision. Again, how far is spread doesn't really tell you the full picture. When you want to talk about how the precision, you are going to look at the something called the relative spread. We are looking at the spread related to the average, the center point, to the average of the center point. So assume the center point is right here, but the spread is really, really close, and then the distance should be very, very, very small. And then when we take the relative spread all over the mean, the percentage will be small as well. So essentially, we are going to do a similar correlation or analysis on the spread with respect to our average. Okay, say our average is 6.1. That should be on the denominator. 6.1 seconds, and our spread will be 0.3 seconds. So we are going to be looking at our spread over at our average, or in other words, we can put our standard deviation over our mean. We have a relative standard deviation, and then we can compute the relative percentage of relative percentage or spread or relative standard deviation. So if I do a rough calculation, we will have around 4.9% over here for relative standard deviation or relative spread. Okay, so for this case, if I set the threshold to be 5%, then the spread will be considered to be very, very minimal, and we can say that we have a precise measurement. Okay, however, if we are doing another type of measurement, for instance, we are going to measure the thickness of a coin, and say I have a really thick coin, it's 0.5 for the average thickness, so 0.5, say is in millimeters. So millimeters. If we do the same calculation or same analysis, we will see that it will roughly equals to 6%. Okay, 6%, 6.0%. Okay, so from here we can conclude that because already exists 5%. We conclude that this measurement, if we measure a coin, the average is 0.5, but the spread is 0.3. Our measurement will not be precise. So therefore, the precision depends on the spread and also the value of the mean. Alright, so let's come back to our questions. So we want to expand our measurement over here. in terms of the mean and also the spread, so we can have an idea of the precision and also the accuracy. So from here, we just need to present 6.1 second average plus and minus 0.3 seconds. The proper way of doing that will be 6.1 plus and minus 0.3 seconds. And that's what they are doing over here. So first of all, they find the average, and then they find the spread, and then they will represent that in our mean plus and minus of spread, which can be standard deviation. Alright. Okay, so we can move on to question 3. Question 3 will be a little bit complicated. Okay, so we have to calculate the fractional uncertainty for the speed of bullet. It covers a distance of 155 plus and minus 0.5 meters. 0.5 meters. Okay, so from question 1 and question 2 over here, we first learn how to present our measurement, just in single measurement in the mean and the spread, the standard deviation. For question 3, we actually look at how to combine different measurements together, and we have to see how the uncertainty or the spread propagate through the calculation. Okay, so we are looking at the speed of bullet. We have the distance, and also we have the time. So how to find the speed? The speed will be equals to the distance, which is d, over time. So this will be the mathematical equation or mathematical operation. You are going to find the distance and time. So from here, you're going to plug in 154 meters divided by 0.4 seconds, and then you will have a corresponding result. Okay, this is normally that what you learn in high school, maybe in high school, maybe grade 11, grade 12, but we are much more be careful, pay attention to the uncertainty in the measurement. The uncertainty of measurement in distance will be 0.5 meters, and also the uncertainty of the measurement will be 0.05 seconds. Okay, so those uncertainty will combine with each other and propagate through to the result. So that's why we have to do a uncertainty or error propagation calculation to find the corresponding uncertainty at the end of the final answers. Okay, so when we are taking mathematical operation, multiplication, division, multiplication or division, we are going to look at the fractional uncertainty, or you can say the relative uncertainty of individual measurement, and then we are going to combine them. So the equation is over here. If I'm going to elaborate, is that the uncertainty in our speed or velocity. Let's case speed I go use as the fractional uncertainty of the speed over the actual speed will be equals to the sum of the fractional uncertainty in the distance and the time. So it will be equals to the distance plus the uncertainty in time. Sorry, this should be d over here, and this should be d. Okay, so we just need to plug in our uncertainty over the actual measurement, uncertainty over measurement, multiply both together, and then from here we will be able to know the relative uncertainty in the velocity or in the speed we calculate. So from here, you just plug in number over here, we find that equal to 0.128. This will be called the fractional uncertainty or relative uncertainty. Okay, but how can we find the actual uncertainty number for the speed? Okay, so we have 0.128. It's pretty easy. We just need to multiply our speed by the fractional uncertainty or the relative uncertainty, and then we will have the uncertainty of the speed, and then we will expect our answer in the speed plus and minus the uncertainty of the inner speed. All right, so that's the okay. So from here, we went through how we express different, I would say the same measurement, but with different replicates or different trial in mean plus and minus the spread will be the standard deviation and the uncertainty. And then we're going to look at, okay, if we have two separate type of measurement, for example, distance and the time, how can we combine two together when we're finding out the speed? At the same time, how the uncertainty combine each other to propagate to lead to the uncertainty in the final answers. Okay, so to conclude the topic number 2, every scientific measurement will have certain amount of uncertainty in the final result. Yeah, it depends what equipment you're using. The uncertainty will be small, and also depend on your experimental design. So yeah, the uncertainty you will see all the uncertainty in all the measurements, and then at the end you will combine everything together, and the uncertainty will propagate. And the uncertainty can be measured in terms of accuracy or precision, or in other words, the accuracy and precision can be represented by the uncertainty of your measurement. Okay, so the final result in the laboratory measurement is obtained by keeping in mind the range of uncertainty parameter. So when you actually proceed to work on your experiment, when you take a measurement for the mass, the volume, something like that, you should be able to have an idea that you have to keep the range of they have a specific range of uncertainty. Okay, so all right, so we still have 3 minutes. I think I will call it the end of today's lesson. We will continue on the significant figures and calculation, and we will look through how we can express the uncertainty measurement in terms of the significant figures, and also how the significant figures become significant when you're moving on the calculations. Okay, so if you don't have any questions,